turn it over to Joe. And I'm just going to preface this a little bit, and Joe, you can correct me, but there's been a lot of discussion about some of the work that Joe is doing, funded through the NOAA MAP program, on temperature extremes. He'll explain it to you, but basically we refer to it as temperature IDF curves. We've found out, like many times at NOAA or any other federal agency, that the Weather Service was notionally developing something along these lines. We were hoping to have someone from the Weather Service join us today to talk about that initiative. I think Joe's been in touch with them. Obviously, they couldn't join us today because of the shutdown, but what I've asked Joe to do is just to kind of give us a preliminary sense of the work, where he thinks it's going, what interactions he's had with other groups around temperature products of various needs. Um, Joe is a member of ASCE 32, which is the frost-proof foundation design standard. I know I didn't get that correct. So this is a great example. Joe's a great example of we're having more and more climate scientists join these committees. I think, from my perspective, I would say that whatever goal we set out when I first sat down with Ben D'Angelo to talk about ASCE and NOAA, or for that matter, when Debbie Lee was having conversations with folks within NOAA and ASCE about this kind of work, we've made real progress. So I think it's tough times right now, but I feel very happy with where we are, barring funding issues and so forth and so on. But anyway, with that, Joe.
Okay. So yeah, I'm gonna try to make this short. Actually, I have like 14 slides, but I'm gonna go through them fast because some of them are a little more technical than I think what Dan wanted here. Um, Very quickly, uh, NOAA Climate Program Office modeling. No, I don't know what MAP stands for except predictions. Anyway, it's basically I don't really know what MAP stands for, but they fund a lot of forward-looking climate work. They get this Private Climate Services grant. It's a multi-institutional grant. Russ Vos is the primary PI on this, and the CU Boulder part that I'm leading, it has three really three tasks beyond the sort of engaging with engineers. It's non-stationary analysis of the air freezing index, which we'll talk about a little bit for engineering applications. Moving on to intensity, duration, frequency analysis of daily maximum and minimum temperatures. And there's some engineering applications, but not so many. And when it was put together, there was thought there was heat health possibilities, but we'll talk about it at the end when I talk about some coordination. There was also an element of applying the same kind of IDF analysis to drought indices. And you'll see that the infrastructure, the statistical infrastructure we're building, would make that fairly transparent to do. Now, why is this a problem for temperature? Why is this not just, okay, you shift this warming 3 degrees, you shift everything by 3 degrees? This is a complicated diagram. The top row shows the mean, the variance, so how much it varies, and the skewness, how much is asymmetrical, how much warm events are different than cold events. And so three statistical quantities. The bottom graph shows from a published work projected changes. And you see it's not just the mean shift, red everywhere it warms, pretty much, but also in many areas, the variation gets smaller. So that might compress you at one end and make it more extreme at another. This is for wintertime. There's also a summertime graph I didn't show here. We're looking at both cold and warm extremes in this. And the skewness is how much you get like surprises on the warm side or surprises on the cold side where you have rare but very extreme events. So these three things matter, and they're all, according to our best estimate from climate models, changing in a directional manner. Now the details when you're in the middle of North America where it flips sign and it changes, where the white areas where there's not much change, those get a little bit difficult to deal with. But as you can see, the far north is generally different than the sort of southern mid latitudes, 20 to 40 degrees north. This all just makes it complicated. That's the only point I want to make. Um, and it affects the extremes, which is what we care about mostly for these applications. Now, I'm going to talk about the first part very briefly, the air freezing index, because that's what we focused on first, and frost protected shallow foundations. And that is basically you can build a foundation that's not as deep as the frost depth if you insulate it and keep the frost from penetrating. I mean, that's what it comes down to. Very important in cold regions engineering. When you say that water drives everything in cold regions, also temperature. I mean, the thawing of permafrost, and climate scientists hanging around that the cold regions engineers I know to say thawing of permafrost, not melting of permafrost. Frankly, learning those communication subtleties is part of being embedded in these committees and working. I don't want to say too much about this, but I'm on the committee because of this. They're updating this. They're trying once again to update it. The air freezing index part, there's 4 or 5 of us I'm going to have the first meeting of our subcommittee that I'm chairing, really a task work group this afternoon. Um, the primary interest in this committee is on the materials and how they're applied and how they want to update that for that. And this is, there's very carefully balanced representatives from different industry groups. The those of us in the air freezing index and other climatic um, data, we're trying to see what we can do to deal with trends or and basically also data where there wasn't data before using some gridded products. So this is what's in the standard now. These come from a 1989 work. They were interpolated by hand, not by hand. Well, but they were interpolated using very basic interpolation methods from station observations. And the dashed parts in North Alaska meant that there was really no observation, so they just drew in some contours. And between what was known on the North Slope and what was known elsewhere, we're hoping to improve on this. Um, you'll see. I'm just picking some points of this air freezing index, which is a cumulative index throughout the winter of with some variations about how cold you are below freezing. But it takes into account warm periods and then cold periods and warm periods and cold periods, which is particularly important in CONUS because it doesn't stay below freezing all the time. The dashed line is the global mean surface temperature, so global warming, right? From 1940 through 20 through present. And you can see in general at these places in coastal Alaska, interior Alaska, northern Great Plains, southern Great Plains, there's a tendency for this value to have dropped. And this is the ERA 5 reanalysis. I don't want to talk too much in detail about our data sources. But in general, one expects that as it gets warmer, this freezing index gets, the cumulative amount of cold into the ground or heat out of the ground during the winter should should decrease. But as you can see, there's a ton of variation. These arrows point out that in Alaska, the Pacific Decadal Oscillation, a climate variability, can lead to radical differences from 5-year period over 5-year periods. So you have to take into account that. This is what I meant by variability is important. So that's just some sort of science behind it. We have spent most of our time building our statistical framework to analyze this. And I don't want to go into so many details about this. Oh, I guess I'm not in presenter mode, so you're gonna just see all my, bullets here. Let me see what happens. Probably be a little bit easier to do this in presenter mode. Can you see this now, everybody?
Yeah,
Continue to share. Continue
there
to
you
share.
go.
Yep,
You should see like a book title. There's something
Yep.
yep.
called, I don't want to go into detail except that we're using a sort of a modern statistical analysis framework where you can actually use spatial and temporal covariance. Our temporal covariant is going to be global mean surface temperature primarily. This can be applied historically, and it can also be applied to climate models. Um, there's a special extreme value package. This is extremely well done and statistically supported through the R statistical package, but we are actually using Python to call the R statistical package. It works on grids. We've got it, working on continental scales on those grids. Um, it kind of has self-determines the statistical um, cross-validation, which is really nice. And the reason we want to do this is because if you just use like the last 30 years, you're throwing away a lot of your data on variability. And as I said, variability is really the important thing. So that's the reason that we've chosen this. And you can simplify it, you can reduce it to linear regression, you can complexify it, and that's part of the challenge. So here's our grant goals. This is the progress so far. Method development. We've spent a lot of time on that. The other person on this grant, Gael Ervieu, who came on, since I couldn't hire someone externally, we found someone internally who turned out to be a fantastic fit for this. Um, it was her suggestion to use this statistical package and rather than piecing these things together piecemeal. Air freezing index, we pretty much computed it using the so-called US method, which has some bells and whistles that are not simply a freezing index. Python code available for that. We plan to make the code available. We're vetting that to make flexible so it can be applied to many things. We're QCing that product. We want to put that product out first, just the yearly values. Our extreme value analysis is going ahead, but there's a lot of technical issues that I want to explore primarily with the ASC 32 committee, who has at least one person who was on some of those papers in the 90s and would be a fantastic source for making this applicable to engineering. The IDF analysis is just starting, but we've done our methodological development, with an eye towards applying it to the daily temperatures. There's a very interesting use case that came across that I'm using to start with, which is the coldest hour of the year. Gas utilities need that. Natural gas utilities need that to plan. The 30-year return period, coldest hour of the year is one thing they use, which is basically the minimum temperature on the coldest day of the year. And so it's a daily, single day rather than a accumulated seasonal one. And I'm going to show you a few interesting things later on about that. It's sort of a microcosm of the IDF. Um, Let me see. Oh, well, this was the one I was going to show you, but I just talked about that. So before we get back to that, this is daily temperature skewness map that was then a graduate student, now a postdoc, working on other projects Nils Bjarke made. Um, Again, long tails, potential for surprise. This is summertime temperature observed. Portland Airport, of course, where there was this tremendous heat wave a few years ago that had a lot of mortality associated with it. You can see this long tail, these extremely rare but extremely large events on the warm side. All these blue dots show where that's likely to happen. And again, the heat wave hit all of the Pacific Northwest and also southwestern BC. Um, sorry, I just wanted to show you that, inland, oftentimes the skewness is the opposite direction. So it's compressed on that upper end. And so that has implications. So that's why it's difficult. Cold outbreaks and heat waves are often large departures from what's otherwise a stable climate. The trend in the coldest hour was very interesting. They were asking like, well, is it getting warmer? Do we need to regulate gas utilities differently? What's going on? And you find out over much of the country, the coldest team in with the upper plots showed not much change. As a matter of fact, a little bit worse, which is not what you would expect from climate change. And that's again because of the shift in the variation, not just the shift in the mean. The warmest temperature shows in the east, this hottest hour shows this basically well-known warming hole in the east. Summertime maximum temperatures have not gone up in much of the country, statistically, at least for the daily time scale, because of increased cloud cover and precipitation. Um, Part of this is we're exploring. Dan asked me to mention some of the other products that are out there. I just want to mention them that might be impinge on that might sort of be relevant to this. There's this Climate Explorer from UNC Asheville, which uses CMIP5 data. It aggregated to the county level, which is not great for like San Bernardino County in the U.S., which is as big as Rhode Island, I believe, or maybe larger, with 11,000-foot mountains and below sea level um, deserts. Um, But, in our Ground National Lab, we've gotten a lot of requests like, what are they doing? How does this relate? Currently, the way they have it deployed, it doesn't have much for these kind of extremes that engineers or heat health might use. NASA power data, again, is primarily reanalysis, and their freezing index is calculated, but it's not the one that's used in the standards. And CalAdapt is only for California, perhaps Nevada. Very interesting, but the new version, which will be very flexible and kind of hard to use for certainly for an engineer, will it actually looks the most promising as far as the approach, but again, it's only regional. So in summary, temperature IDF, we're going to focus primarily on gridded products as part of the proposal, but the code will be applicable to station data. Um, we're going to be looking at the incline grid for the CONUS, which is 4 kilometers, which should be pretty good as far as resolution in topography goes and coastal areas go. Classical extreme value analysis. Global warming level is the covariate, but you can back out time and scenario if you want. And maybe perhaps we'll probably, present it that way if that's what's a demand for that. And the projections will focus on really getting the statistics of what's happening and the physics of what's happening in these models correct, and then applying that to a historical baseline. So it's sort of a very, it's a change factor approach, but it's done with a little bit more attention to the statistics. Coordination, NCI Industry Proving Ground. We're talking to them about potentially serving some of the early products. Their work ends in a couple years, a year, I think, a year and a half. Again, the ASC 32 update committee, of which I am a voting member now. And this is what the last is what Dan referred to, Adrian Lopez, who's working on heat indices. Uh, he's focusing on heat index that involve humidity, heat, oftentimes some estimate of solar radiation. So really focused on some of the indices for human health. But he's doing it from station data and looking at hourly data, which is extremely complex just to get the station data in order for that. We've talked and we're both very interested in cooperating on methods, potential data sources, and perhaps doing a station analysis for just the basic temperature. So I just wanted to give that to you and let me stop sharing and see how we're going here.
No, you're great, Joe. Thank you so much. I was trying to give you an out. I didn't want to put pressure on you to develop too much content, but you, as usual, over delivered. So that's great.
Um, part of this is I have to deliver it this afternoon for our 32 meeting.
Oh, okay. Well, there you go. You didn't need to
So
post that.
I'm doing double duty here.
Anybody have any questions or comments for Joe?
Hey, Joe, I have a question.
Yes.
Do you obey? So, a lot of data, do you have enough long-term record, not the graded data, but particularly the heat index? Is that long enough to look at things like non-stationarity?
So, I mean, that really is what Adrian and I are going to be talking a lot about because we're both, um, he's coming up to speed on a lot of these non-stationary extreme value analyses. And I've been kind of immersed in that for several years now. And as long as you can aggregate similar spatial regions, you can gain some sort of non-stationarity. The problem with heat index is the other variables, humidity, solar
Yes.
radiation. They'll be estimated, and there's ways to estimate those. And part of the challenge there is, are those good enough? Are those
Hmm.
good estimates, right? That's the reason I've been reticent. Matter of fact, the reason why we focus purely on temperature extremes. Um, for example, heat health is not, not ignorant of temperature. They just would like these other things. But if you could say, look, there's the chance of 3 days where the minimum temperature is above 80 degrees Fahrenheit, they will know that that will have, heat health, strong heat health impacts.
Hmm.
And I don't want to say fortunately for us, but not fortunately for the people impacted. Minimum temperatures behave much better than maximum temperatures during the warming. There's pretty fairly widespread warming in minimum temperatures because of the humidity increases. The humidity increases and the cloudiness and the rainfall, of course, have tamped down the peak maximum temperatures, but not the heat index. The heat index has gone up because it's hot and humid. So
Right.
we're going to work together on that. And, frankly, most of the non-stationarity, the forced non-stationarity has happened in the last 40 years when we have good data.
Hmm.
Um, um, I'm reticent to use only station data, first of all, because that would have taken up our entire grant, just getting the station data in order, and he's working on it. And second of all, Stations move. The gridded products try to homogenize the data at the cost of specificity, but they give you advantages that the station data doesn't. So there's, I think, looking at both and having both of us simultaneously coordinating and working on this is kind of like a dream situation. So I don't have to do what I don't really want to do because it's difficult on the prep side, and he's doing what he's really great at, and also combining our statistical knowledge. So I think it's going to be really good.
Mhm.
Excellent. All right. Any other questions or comments for Joe?